So now we're going to look at solving for the kernel and image of a linear transformation based on the um, uh, matrix, based on the matrix representation of the linear transformation. So the first thing that we're going to do is we're going to talk about where this matrix comes from. This matrix comes from looking at, or is equivalent to A t of V1 plus B t of V2 plus C t of V3 plus D t of V4 equaling 0. And then when you have this representation, you're asking, okay, when does this equal 0? And this gives you the system of equations, V alpha T alpha beta equals 0 alpha. So if if the vector A, B, C, D is a solution vector, then V alpha equals A, B, C, D. So this means that when we get our solution set to this homogeneous system, we have to use alpha to convert it to determine what is my actual resulting vector. So to start though, we're just going to solve for the basis of the kernel by setting this equal to 0 and solving our linear system. Okay. First thing I'm going to do is I'm going to annihilate the column. I choose this to be my pivot entry. I put it in that row and I use it to zero out. So R2 minus R1 replacing R2, R3 minus R1 replacing R3, and R4 minus R1 replacing R4. Gives me the first row doesn't change. Then it's 0, minus 1, 0, minus 1, 0, 0, 0, 1, 1, 0. Now 0, 1, 0, 0, 0. What I'm going to do is we could either take this one or this one. I like swapping the rows here. So I'm going to choose this to be my pivot because it's already 1. So I'm going to swap, take R1 or R4 and swap it with R2 to give me 1, 1, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, and 0, minus 1, 0, minus 1, 0. Now I'm going to take R4, add R2 to replace R4, 1, 1, 1. And I'm going to take R1 minus R2 to replace R1. So it's 1, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, minus 1, 0. Okay, now this is my next pivot entry. I'm going to use it to zero out my first row. So R1 minus R2, R3 replaces R1, gives the matrix 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, minus 1, 0. And now I'm going to do 1 over minus 1 times R4 replaces R4, giving 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0. Now I need to eliminate that column. So R4, R3 minus R4 replaces R3, gives 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0. Right? Which gives me the homogeneous system, which implies 0 TV1 plus, or plus 0 TV2 plus 0 TV3 plus 0 TV4 equals 0. That is what this system represents. Okay? Because remember, my variables are how much of each of these vectors here using the output basis, how much of the first vector plus how much of the second vector plus how much of the third vector. But what I've done is I've looked at 0 A TV1 in beta, A TV2 in beta, plus C TV3 in beta, plus D TV4 in beta equals the 0 vector in beta. It should be a beta. So now we got to look at, okay, what's my kernel and what's my image? Well, let's start with kernel. We're going to start with our discussion of kernel of T. And we let A, B, C, D be a solution vector. Well, we have this system. What we have is we have A equals 1, B equals 1, C equals 1, and D equals 1. Our free variables, there's none. And our basic variables, we have A, B, C, and D. Okay? So from here, A equals 0, B equals 0, C equals 0, and D equals 0. From here, we can update our solution vector. A, B, C, D equals the vector 0, 0, 0, 0. That's our solution set. So our set of solutions is the set containing the 0 vector. But remember, if V is in the kernel of T, then V alpha equals A, B, C, D. And here our solution set is the set containing the 0 vector. So here, this equals the vertical vector 0, 0, 0, 0. Well, this implies that V equals 0. My first coefficient is, this tells me 0 V1 plus second coefficient is 0, 0 V2 plus 0 V3 plus 0 V4. Okay. Well, I now need to convert this using my basis. So V is going to equal A times the vector 1, 1, 1, 1. Or sorry, 0 times that vector, plus 0 times the second vector, which is 1, 0, 1, or 1, 0, 0, 1, plus 0 times the third vector, which is 0, 1, 1, 1, plus 0 times the fourth vector, which is 0, 1, 0, 0. Which equals the 0 vector. Right? Now, what I'm doing here is I'm taking this vector, and that represents the coordinate vector. So when V of alpha equals those entries. V doesn't necessarily equal those entries because V is not because alpha is not the standard basis. We need to convert to what V would be using our basis alpha. The same thing goes for the image of T. Well, if we look at this and we look at our image, our free variables, if we look at the image of T, the basis is the vectors corresponding to the basic variables. Okay. Well, we know that TV1 of beta equals 1, 1, 1, 1. TV2 of beta equals, from our matrix, 1, 0, 1, 2. T of V3 of beta equals 1, 1, 2, 1. And T of V4 of beta equals 1, 0, 2, 1. Well, this means that T of V1 equals 1 times 1 1, 1, 1, plus 1 times 1, 0, 0, 1, plus 1 times 0, 1, 1, 1, plus 1 times 0, 1, 0, 0, which is equal to, we add these all up, it's 2, 3, 1, 3. So TV1 is 2, 3, 1, 3. TV2 is going to be 1 times the vector 1, 1, 1, 1, plus 1 times the 0 times the vector 1, 0, 0, 1, plus 1 times the vector 0, 1, 1, 1, plus 2 times the vector 0, 1, 0, 0, which equals 1, 1, 1, and then 1, 2, 3, 4, and then 1, 2, 2, and 3. T of V3 equals, well, it's 1 times 1, 1, 1, 1, plus 1 times 1, 0, 0, 1, plus 2 times 0, 1, 1, 1, plus 1 times 0, 1, 0, 0, which, if you add them all up, gives you 2, 4, 2, 4. And our last vector, T of V4 equals 1 times 1, 1, 1, 1, plus 0 times 1, 0, 0, 1, plus 2 times 0, 1, 1, 1, plus 1 times 0, 1, 0, 0, which equals the vector 1, 2, 3, 4, 1, 2, 3, 1, 2, 3. So that's T of V4. So because my image is the span of all of these vectors, my image is going to, of T is going to equal the set TV1 through TV4 by our theorem, meaning it's going to equal the set 2, 2, 1, 3, 1, 4, 2, 3, 2, 4, 2, 4, and 2, 4, 3, 3. And yes, in this case, because the image of T, it has 4 basis vectors, it's mentioned 4, you could use the standard basis. And yes, because the kernel was all zeros vectors, the answer is going to be 0. But if we give you some sort of wrinkle in this set where the image isn't all the vectors and the kernel isn't all the vectors, this is how you'd convert it. You take your outputs and say, okay, the coordinate vector representation of the outputs are these vectors. And use that to figure out what the actual basis vectors are for the image. And same thing here. The coordinate representation of my V alphas for my kernel are these. What are my actual V alphas? And that's how we figure out what our basis for our kernel is and our basis for the image. So the basis for the kernel, the basis is the empty set because it's the set containing no vectors. And for the image, the basis is the set of these vectors.